In this video, we're going to do two things. First, we're going to introduce the kinematics equations for constant acceleration, and then we're going to look briefly at how to lay out typical physics problems. So let's begin. In a previous lesson, we did an exercise where, starting from basic definitions, you had to derive equations to solve particular kinematics problems. Here are three of the problems that we met in that lesson and some of the subsequent practice exercises. And here are the solutions to those problems that we derived. If you look closely, you may notice that all three of those solutions are actually the same equation, and it's usually written this way. If necessary, pause the video and take a quick look and convince yourself that all four of those equations are the same equation, just rearranged to solve for a different variable. In fact, if I gave you 100 of these type of kinematics problems and asked you to derive an equation to solve them, you would find that you actually end up deriving the same few equations every time. In fact, there are 5 of them, and here they are. They're known as the kinematics equations for constant acceleration. And if you look carefully, you'll see they deal with 5 kinematics quantities. Most motion can be described using these 5 key ideas: displacement, time interval, the velocity at the beginning and the end of that time interval, and the object's acceleration. And each of those equations tells us how 4 of those 5 variables are related to each other. So between them, we can solve almost any kinematics problem that we want to, as long as we know 3 of those things about the motion that we're studying. We'll explore the kinematics equations and their use in subsequent lessons in a lot more detail. For now, we're just going to look at one sample problem. It's a very simple one, and we're going to use it mainly to focus on laying out of problems. So here it is. We have a ball rolling down a hill at 4 meters per second, and it's accelerating by 2 meters per second every second. We want to know what will its velocity be 5 seconds later. When you're asked to show your work on a problem, there are 2 things I'm looking for. One is getting the right answer. Obviously, that's important. But equally important is being able to explain to your reader clearly how you got that answer. So layout matters. You know from your own experience how hard it can be to follow mathematical reasoning, so you don't want to make things harder for your reader by laying it out in an unfamiliar way. There are certain conventions to follow. Here's the minimum that I expect. The first thing I want to see is the list of information. What do you know? What do you need to know? So in this problem, we're told that our ball is rolling down the hill at 4 meters per second. That's its initial velocity. Velocity is a vector quantity. We need to indicate directions here. So how do we do that? Well, our ball's moving in a straight line, so you know that when there's only 2 opposite directions, we can use plus and minus to indicate them. Which one is which? Well, it's arbitrary. We could do it either way. I'm going to do it this way. I'm going to call up the hill the positive direction and down the hill the negative direction. I could have done it the other way around. I just chose to do it that way. So our initial velocity is not 4 meters per second. It's 4 meters per second down the hill. What else do I know? It's accelerating. It's accelerating at 2 meters per second. Which direction? Well, as it goes down the hill, it's speeding up. It must be accelerating in the same direction that it's moving down the hill. We're talking about a time interval of 5 seconds, and we're interested in the velocity at the end of that 5 seconds. So there's my list, the information I know and the information I need to know. Now I can do my calculation. Begin with the relationship. I need an equation that says VF equals, and on the right-hand side, I want initial velocity, acceleration, and time interval. Well, that's one of my kinematics equations. One of them says final velocity is equal to initial velocity plus the acceleration multiplied by the time interval. On the next line, I want to see that you're using the right values in the right place. So the second line is pure substitution. Basic mathematical layout, you work down the page, not across the line, equal signs underneath each other. My initial velocity is -4 meters per second. My acceleration is -2 meters per second, and my time interval is 5 seconds. Notice signs matter and units matter. We're not working with numbers, we're working with measurements. Equal signs underneath each other. The next step is to calculate the answer. Notice this isn't about math. The math is all math you should already know how to do. This is about the physics. I need to see your logic. If you need to play around with math, you can do that on your calculator or on a piece of scrap paper on the side. All I need to see here is the answer. -2 times 5 is -10, and we end up with meters per second, plus -4, we end up with an answer of -14 meters per second. The majority of the calculations you do in introductory physics are going to be 3-line calculations. First line, show me the relationship you're working with. Second line, show me that you're using the correct values in the correct place in that relationship. Third line, give me your answer. There's one more thing. You need to show me that you understand what that answer means. So I want to see a verbal explanation of the answer. By verbal, I mean no signs, no positive or negative signs, no other signs. You have to show me you understand what those signs mean in the context here. So the question said, what was the ball's velocity after 5 seconds? So our answer is going to be something like, after 5 seconds, the ball is rolling down the hill at 14 meters per second. Notice no signs, not -14. The negative means something. The idea is to put into words what that negative means. In this context, the negative means down the hill. So there you go. On a basic, simple, calculated problem in physics, this is what I expect to see at a minimum. A list of what data you have and what you need to know. Calculations laid out according to a conventional manner, equal signs underneath each other, 1 step per line. And then a verbal statement of the answer that shows me you understand what the mathematical answer means in that context. So there we go. Our list of knowns and unknowns, work down the page, equal signs underneath each other, show directions and units, they matter, and give me a verbal statement of your answer. So in later lessons, we'll explore these kinematics equations a little bit more, but for now, that's enough.